We had last week, that the Maui Marine Resource Council had last week, where we put our first prototype group of oysters into Maui Harbor. So please watch and enjoy.
Inama po may kalagyan para pa may kukuy kalabay. Inama po ito yung mga po ito ng alo. Iya kawin pala ni Nulin pala ni Corporal. Iya po mga po. Maui Marine Council. Imaramo po. Ikanauhan. Uli ka lang ni ulo ka no. Ulo ka pa kayo na. Maui Nulin kama. Humay ka ike. Humay ka kayo. Humay ako maay. Umay mga puno, umay papuluay mo kumaana. Imahari yung nakapuno ka ito na Maui Nui kama. Imakaala, malamay yun. Maui Nui Marine Council.
So my name is Amy Hodges. I'm the Programs and Operations Manager with Maui Marine Resource Council. And today we're here at Maui Harbor because we just had a blessing and installation. First time for our pilot oyster project. So the oysters are a bioremediation project meant to help clean up and clear the water. Ultimately, we want clean, healthy water for the benefit of our corals and fish. The oysters we put in today were about 500 of the Pacific species. They were born and raised at the Hilo Pacific Aquaculture and Coastal Resources Center with Dr. Maria Haas and her team. And they brought them over today for us to install here at the harbor. The oysters are helping to filter and clean the water by removing phytoplankton and sediment from the water column. Ultimately, that will help the health of our fish and reef ecosystems here on Maui. So we're starting the pilot project here in Maui. We started with 500 oysters today. We'll monitor them regularly for their health, make sure they're surviving, check them for predation, check them for any biofouling that might be occurring on their shells and on the cages. And after about a month, we should have a good idea if they're able to survive here at the harbor, and then we'll add another 500 to make it a 1,000 oyster pilot project. We'll continue monitoring them through the course of the year while our partners at the Pacific Aquaculture and Coastal Resources Center are busy growing out the next batch of oysters that we could add at the end of the year. At the end of the year, we could possibly be adding some endemic species of oysters as well. So I just want to definitely thank all of our supporters and partners that made today possible and made this project come to fruition. It has been a bit of a process, just making sure that we have all of our permits and right of entries and everything in place, and funding for the oysters and the project. So it's the County of Maui Office of Economic Development, Councilmember King. We have Hawaii Tourism Authority. We've got our partners at the Pacific Aquaculture and Coastal Resources Center. We've got Oahu Waterkeeper by Viola Hawaiian Islands. We have our friends at DLNR and Dobor, and our friends at the Department of Ag. All of these agencies and Division of Aquatic Resources, all of these agencies and partners all came together to make today possible, and it's been a really positive experience. Everyone has been really on board and supportive of this project. It's just a matter of getting all of our ducks in a row so that today could happen. And now moving forward, it should be smooth sailing. We really anticipate it to be a successful project.
Mahalo na kupuna. Mahalo na kupuna. Kuiwimi is mahalo, ia'u aloha. Kuiwimi is mahalo, ia'u aloha. Mahalo, ia'u aloha. Three claps, thank you.
Very cool. Our second video for you is about our water quality monitoring program, Hui Okawai Ola.
Beautiful west side of Maui. And in this video, we wanted to really break down a little bit about the Hui Okawai Ola initiative.
Hui Okawai Ola means Association of Living Waters, and it's a unique community-based, volunteer-based program established in 2016 by Maui Nui Marine Resource Council, the Nature Conservancy, and the West Maui Ridge to Reef Initiative to give our community the information and data needed to work for clean ocean water. Thanks to the efforts of more than 35 dedicated volunteers, this program regularly monitors 41 shoreline locations in South and West Maui. We test 19 sites in West Maui, from Papalauapali to Honolua, and 22 sites in South Maui, from Ma'alaia to Wahi'i. The volunteers work in the early morning hours, gathering water samples at knee depth and conducting initial testing on-site in mobile labs in their cars. Additional testing of the water samples take place in a lab space donated by the Hawaiian Islands Humpback Whale National Marine Sanctuary and Lahainaluna High School. And after that, the samples are frozen and shipped to Oahu for nutrient testing at the University of Hawaii. We all value clean ocean water for swimming, surfing, diving, snorkeling, paddling, fishing, and playing at the beach. Our coral reefs also need clean water to survive and thrive. You may be surprised to learn that much of the water along Maui's south and west shorelines is impaired, meaning it doesn't meet the Department of Health standards for clean ocean water. To achieve clean ocean water along our shorelines, our community needs to understand where ocean water quality is impaired and why. That's where Hui o ka Waiʻola comes in. We work closely with the State of Hawaii Department of Health Clean Water Branch to ensure that our data is quality assured and can be relied upon by the community. The Department of Health provides our data to county, state, and federal agencies, local researchers, and community groups, and the public. You can also find our data and helpful graphs summarizing our findings for each of the 41 beaches at www.huiokawaiʻola.com. For all of our supplies, equipment, shipping of samples, and administrative support to coordinate the volunteers, it costs $4,000 per site per year to continue this program. Our community's support makes it possible. If you value clean ocean water, we ask you to help sponsor water quality testing at your favorite South and West Maui beach. You can learn more at www.mauireefs.org/water. And special thanks to these sponsors who also help make this unique program possible.
With that, guys, check out MauiReefs.org if you'd like to learn more on how you can participate, how you can help out, and we'll see you guys very soon. Aloha.
Okay, well, after that musical interlude, let's get to our main speakers. To introduce them, I'd like to bring up Stephanie Stack, who is the Chief Biologist at the Pacific Whale Foundation.
Thank you. I thought I was off the hook and didn't have to speak today. I just want to say thank you so much to our host, the Maui Nui Marine Resource Council, for inviting us here tonight, and thanks to Maui Ocean Center for offering this space to us. And thanks to all of you, the community, for all your support. I'm going to introduce three really amazing, talented, and intelligent researchers that are going to give a great talk for you today. It's been a really amazing week for the whale community here in Maui. I hope you all heard the news that we saw a new baby being born yesterday off Lahaina. So we have three speakers. I'm going to introduce the first one. This is Jens Currie, my colleague at Pacific Whale Foundation. And then we're going to hear from Lars Bejder, who works at the Marine Mammal Research Program at University of Hawaii's Hawaii Institute for Marine Biology on Oahu. And you're also going to hear from Adam Pack, who works at the University of Hawaii at Hilo and the Dolphin Institute. So really amazing, talented speakers, and I hope you enjoy. Thank you.
All right, can everybody hear me? Yeah, good. Good evening, my name is Jens Currie, as Stephanie mentioned, and I'm excited today to talk to you about some of the recent work that's been going on, looking at the changing trends in humpback whales here in Hawaii as well as Alaska. And I titled the talk Searching for Answers, and I really want to set the stage right away. If you want to know what happened in the 2015-16 season when whale numbers plummeted, you're about a year or two too early, and we're still at these stages of finding answers. But what we can present today is some of the really great work that we're doing, collaborating across islands, across organizations to look at what potentially drove that change in numbers of humpback whales. I'm going to work on basically setting that stage, bring everybody to the same speed, and learn what happened to our humpback whales since 2013 up to now. And really, this 2015-16 drop is kind of interesting because it coincided with some great conservation efforts, where in 1970, humpback whales were enlisted as an endangered species, and for nearly 40 years they remained on the endangered species list. But then in April of 2015, they were proposed to be delisted and recategorized, and then that was realized in October of 2016, shortly after we saw this plummet in humpback whale sightings. Along with that was a division of the humpback whale population from a global population into 14 distinct segments, as you can see on the map here. 4 of those population segments remained as endangered, 1 was moved to threatened, and 9 were considered recovered, or not listed or not at risk. And that population includes the Hawaii population, which is number 4 on the map here, and that's the population that you're going to see out here that comes to the Hawaiian Islands. It also includes whales that go to Alaska and BC and British Columbia and Canada. And this delisting and separation of the population really was a true recovery and a really great ecological success story, because we're talking about a population that came from fewer than 1,000 individuals in the late 70s, and then up to the most recent abundance estimates of around 10,000 individuals in the 2004-2006 time period. Everything looked good. We had a tailored approach for population management just for our Hawaii whales. The growth was going at 5 to 6% per year. But what happens if trends change? So if you were here in 2015-16 season for the whale season, articles like this started popping up fairly regularly, and the title reads, "Mystery Absence of Humpback Whales in Hawaii Has Experts Scratching Their Heads." And that's really what was going on, because nobody was studying abundance per se. They were studying other aspects of the humpback whale population. So nobody could truly say, what is the trend? They could just look at their data that they were collecting, know what the population is supposed to be like, and then make deductions from that. And I'm going to quote Ed Lyman here, who many of you probably know, and he said, "We've just seen handfuls of whales in a time when we're supposed to be seeing armfuls of whales." So we ended that season. Everybody was hoping for a recovery in the following season. So we're now in the 2016-17 whale season, and the trends remained unchanged. We still had low sightings of humpback whales here in Hawaii, and then speaking to colleagues in Alaska, we also saw similar trends up there in that 2015-16 season. An example of that is the humpback whales in Glacier Bay and Icy Strait area, work done by the Glacier Bay National Park. And they have whales up there that use that area fairly regularly, and they have very high site fidelity, meaning they come back to that bay year after year. And they actually have 11 whales that for 30 years were seen in that bay every year. They were able to photo ID them, except for the 2015-16 whale season. Lo and behold, all 11 of those whales did not return. So this shows the trend is holding not only for here, but also for work up in Alaska. And so at that point, it was time to meet. And Mark Lammer's in the audience here. He is the research coordinator for the sanctuaries, for the humpback whale sanctuary. Sent out an email to researchers and managers and said, we really need to get together and talk about this issue we're seeing. I will quote him here because I think it captures the meeting that was held in November 2018 very well. He said, specifically, we'd like to organize a discussion to help establish what we, as a research community, currently know where our knowledge gaps lie and what our research priorities should be. And that's really what we spent November 2018 working towards, and is really what's driving the collaborations that you're going to hear about here tonight, and a lot of the work that you're seeing going on humpback whales right now in our waters here in Maui as well as Alaska. And part of that meeting was for researchers to get together and show some of the information, some of the details that they've collected so far to sort of support the theory that there's a change, but trying to quantify that change. How much is the population changing using some evidence that we have? The Pacific Whale Foundation was in the midst of a 4-year line transect survey, which basically means we have transects, which are in the map here on the right. There's 23 transects. They run perpendicular to the shoreline, and we run those transects each year, multiple times per year, keeping everything standardized, such as the effort, the number of observers, the number of times we're sampling each line. And what that allows is for within season comparison of humpback whale numbers, but also between season comparison of humpback whale numbers. Unfortunately, the last year we did it was the year that we saw the slump in numbers, but we do have some great lines of data to show what might have been happening in that time period leading up to the drop in sightings. So we recorded whales along this line transect, 300 meters to the left, 300 meters to the right. We also looked at age class, group composition, and distance from vessels. If we look at what we accomplished in that 4-year time period, we gathered data on 940 humpback whale groups, just over 1,500 individuals. The majority of those were adults, with approximately 250 subadults and calves. And then we completed a total distance of 17,569 kilometers. Just to put that in perspective, it's about the same distance as from here to Hana 200 times. So there's a sufficient amount of effort there. There's sufficient replication. Each of those line transects was sampled almost 30 times within that 4-year time period. So we have a robust data set that can begin to give us clues into what was leading up to this event that we saw in 2015-16. So to do that, we're going to start in the 2012 to 2013 season. The graphs are pretty similar throughout these next few slides, so just to orient everybody, on the x-axis along the bottom, we have the average counts per week. So the counts that you're seeing are average per week, and on the y-axis, you have whale counts per transect. And so if we look at the peak, we have about 9 whales per transect in the week of February 18th, for example. The shaded area shows peak season, so from other lines of evidence and other data we have, peak season here is defined as having 5 whales per transect per week. And we want to look at what peak season is. So there was some allusion to that earlier, and look how that changes throughout the time period. Fast forward to the next year, we already see switching a shift in that peak season to earlier in the time period. And we also see, a reduction in the peak of that season. So we're already beginning to see some trends, which lines up with other lines of evidence that have been brought to this meeting, that the trend actually started in the 2012-13 season, which was the last good year, let's say, of humpback whale sightings. So the red line here is the 2013-14 season, shift earlier in the peak season, and the peak season didn't last quite as long. The trend holds like we thought. The 2014-15 season shown here in green. Again, it shows a smaller peak season. It's still showing fairly early in that, the first week of February, the peak season was already done for that time period. So basically, the peak season would have ended today if we were back in the 2014-15 season. Luckily, that's not what we're seeing out there today. So happy to report that. But this is the big year, the 2015-16 year, shown here in purple. As you can see, it doesn't reach a peak in season. So we have low numbers, everybody's waiting for those numbers to pick up, to come in, and long and behold, it's April, and the whales really didn't show up, and that's really what sparked the concern for the humpback whales here in Maui Nui. We can summarize these efforts looking at the sighting rates, and we see a 54.6% decline. And I want you to keep that 50 to 60% number in mind, because again, some of this meeting was around quantifying the change, determining how significant the drop in numbers was for Hawaii. But interestingly, we can also look at age class components of this decline. And if we look at whale counts here, just to orient you on these graphs, actually there's box plots. And if you look in the rectangular box, that contains 50% of the data. On the x-axis, you have years, and then in the y-axis, you have the average count of whales per transect in that year. The trend holds for whale counts, so regardless of age class, you're decreasing up to the 2015-16 season. And this is really mimicked by the adult and calf counts, where you have that same declining trend over the years. But what's interesting is when you look at the subadult count, you don't see that decrease. And these are all clues that we can use to determine what's potentially causing it, as well as where we should we focus our efforts when we're trying to understand the changing trends in humpback whales. We also had additional lines of evidence, so that was a very systematic, robust way, but it's nice when programs like Pacific Whale Foundation's Great Whale Count, which is a citizen science program, which does a count once a year, now 3 times a year, and it's basically just a snapshot of whale numbers on a particular day. And what we see here are the counts of humpback whales, calves, adult whales, calves, and pods per year for the history of the program. On the left we have 1995, and if you scoot over until you hit that 2015-16 season, lo and behold, you see a plummet in numbers, with the 2013 season being sort of the last good year of numbers. And so if you want to help us with that, it's a great citizen science program. We're having a count at the end of the last Saturday in February and the last Saturday in March as well. So definitely encourage you guys to come out and contribute to this data set that was picking up on the same trends that our systematic research surveys were, with a decline of about 64.5% in sightings from the 2013 to 16 season. We looked at other islands too, so there's researchers presenting from all over Hawaii. So this is work by Adam Franco from the Marine Mammal Consortium, and he's doing land-based surveys of humpback whales. I want to draw your attention basically to the drop from the 2014-15 season to the 2015-16 season. You can see here on the bottom right of the shaded area, red represents calf counts. You can see that as the lowest count it's ever been in the history of recording data there since the 2000s. And whale counts, or adult whale counts, are mimicking numbers that we saw in the early 2000s. So it wasn't just Maui, it was also on the Big Island. And again, quantifying that change, it's around 57.1% on the Big Island. So we're all speaking the same 50 to 60% decline in numbers. Not surprisingly, if we jump to Alaska, they have 51% decline in sightings. So if you look at their historic photo ID data set, they actually recorded, again, similar trends in the 2015-16 season. But in addition to that, they also looked at body condition, and they started documenting skinny whales, as you can see here on the right. Between the 2016 and 18 seasons, they had around 13 to 24% of all sightings were these skinny whales, where you could start to see various parts of the skeleton, you could start to see ribs. But in conjunction with that, you began to see unusual skin conditions. So you saw blotchy, rough skin, bleeding on the pectoral fins, patchy dermatitis, and all these, again, are clues that lead into a story on where we should prioritize our research here in Hawaii to try and answer the question of what's going on. I also want to show that there was a tourism impact as well. So tourism vessels spent twice the amount of time searching in the 2015-16 season compared to the last good season in the 2013-2014 season. This was particularly felt in Maui, so when the whales aren't here, tour boats need to travel a lot longer to find their whales, and they're seeing fewer whales as well. So what did we learn after that meeting? It was a great 2 days. 38 researchers and managers were there, and we considered the potential explanation for the observed trend. We tried to address the knowledge gaps, and we established these 5 priority areas. The first one is the distribution of whales. So are whales no longer coming to Maui Nui? Are they using other areas, perhaps the Northwest Hawaiian Islands? Are they using different areas in Southeast Alaska? That's why we're not seeing them in these bays anymore. So that was a question we decided would be important to answer, to try and put a piece of the puzzle together. We also brought up abundance, reproduction, and survival trends. So if you look at the population on the basin scale, so the North Pacific population, in the entire history of research, there's only been 2 basin-wide population abundance estimates for the species, one in the early 90s and one in the 2004 to 2006 time period. So really, we don't know what's happening because abundance hasn't been looked at in nearly 10 years. So that was brought up as a potential piece of the puzzle that could answer the question of why we saw those trends. Prey distribution and quality. If you can't eat, if your prey isn't where it used to be, you need to go somewhere else. You might be moving somewhere else. If it's not of good quality, you might not be consuming enough to become healthy and make the migration and conduct your life history stages. We looked at environmental and human stressors. I do want to plug Rachel Cartwright's work here, who was able to link the fluctuating reproductive rates that she saw in mom-calf pairs here in Hawaii to various climatic anomalies. So there's already work coming out of this meeting and being shared, so I encourage you guys to check that out. And then finally, population health. And that's really what you guys are going to hear about tonight, because that's the one we're focusing on. That's the one that all the research we're going to share with you tonight is focused on. So humpback whale population is truly a collaborative approach because we're using multiple streams of data, relying on various expertise across different organizations. And the ultimate goal is to increase the assessment efforts of humpback whales, body condition both here in Hawaii and Alaska. And to do that, we're doing photo ID work, we're doing body measurements, and getting skin and blubber biopsy sampling. So why population health? Well, there's an energetic component. So they need the energy to come to Hawaii, that's the first step, but they also need the energy to partake in the breeding ground activities. And so often you see comp pods at the surface. This is a rare chance to glimpse under the surface and see what's going on there. And again, all this work, all this competing to mate by the males requires a certain amount of energy. And so here we have the female in the front, and then we have the male in the back. Hopefully everybody can see and continue to watch which one's the male and which one's the female. They went under the boat in this case here, and then up the other side. And this is what it's all about. So you're either here giving birth, or you're here trying to mate and reproduce. And these are all energetically very demanding. If you're not healthy, you can't really participate in these activities. What you see here is male and female getting cozy, and you'll see this split off, and the reason they split off is there's another male down below that you can't see that's going to come out and basically belly flop on both of them. You'll see some of that behavior here shortly, but again, it takes a lot of energy to move that water, to compete, and to make sure you're the physically fit individual that gets to mate with the female. And so if you're unhealthy, you're not going to partake in that, and maybe you're not making the migration down to Hawaii. And so really we're looking at our humpback whales in Hawaii and Alaska healthy. Specifically, we're going to investigate 3 components: body measurements and condition, and link that to individual characteristics. So using long-term photo ID, we can identify individuals, we can identify their sex, we can identify their life histories, and using that we can begin to piece the story of a healthy individuals. Loop into that a 3rd component, the steroid hormone, lipid, and stable isotope levels, all which are have indicators of health. And we can put those 3 streams of data together and truly say, is that whale healthy on an individual level, and is the population healthy on a population level? And it's a real collaborative approach. It takes a lot of people to do this. You have Pacific Whale Foundation, you have the Marine Mammal Research Program, University of Hawaii Hilo, the University of Alaska in Fairbanks, and the Alaska Whale Foundation, all working collaboratively to answer this one question of, are whales healthy here in Alaska and Hawaii? And I just want to give you guys a glimpse while I wrap it up here of what the field work is out there. Communication is key. This is what a typical field day looks like. We have a comp pod group of 16 individuals here, 3 cameras going, there's a drone in the air, and 2 data recorders that are collecting all kinds of data that's streaming in from the observers. So if you listen here now, you'll hear that dialogue going on. So it's fun to work out there with the whales. It's great to see them, but really what we're after is getting that data. And all the data that we're getting is going to help answer some of the questions that my colleagues, Lars and Adam, are going to talk about. But before we bring them up, if you want to help out some more, help these humpback whales, you can help spread the message and the word. Take what you learned today, share it with somebody else, and learn about the humpback whales. You can adopt the humpback whale with Pacific Whale Foundation and support the research you're going to hear about here tonight and the research that Pacific Whale Foundation is doing. You can become a member as well. You can donate your photos. So each year we get 200 to 300 fluke photos from the public that really helps supplement our catalog and allows us to determine those life histories of those individuals through photo ID. And you never know when that one photo ID is really going to put a piece together for you, so we encourage you guys to do that. If you're out in the water, please follow some sort of guidelines, such as the Be Whale Aware guidelines. Make sure you're operating safely around those humpback whales. If you want to stay informed and follow us, you can just take a screen grab of this. There's lots of great stuff going on up there. Talk about any of our research here in Hawaii, Australia, Ecuador, this project, our collaborators. We put it all up there for you to share, stay up to date on what exactly we're doing here in Hawaii's waters. And finally, I'm just going to end it with a thank you to all the team members that were involved in this project, our collaborators here, Pack Whale Eco Adventures, whose proceeds support the research we're doing, and of course Maui Ocean Center and Maui Marine Resource Council for hosting this great event this evening. So with that, I'm going to wrap it up there and move it right along to Lars.
Thanks, Jens. Good evening, everybody. Thanks for coming. It's a true honor to be here, so thank you very much for taking the time. My my name is Lars Bejder. I have somewhat recently relocated here to Hawaii 2 years ago. I spent the last 15 years in Australia studying whales and dolphins down there, and now based at the University of Hawaii at Manoa on the Manoa. So great to be over here on the beautiful island of Maui. Today I'm going to be talking about, like again said, a really collaborative project with the Pacific Whale Foundation, Adam Pack from the University of Hilo, Hawaii Hilo, Alaska Whale Foundation, and two other groups, Stanford University, that are helping us with some of our tag work that I'll be speaking about tonight. So overall, I'm going to be talking about work that we're trying to develop what's called a bioenergetic model for what it costs to be a whale. So how much energy do you have to intake, and how much does it cost to migrate between these large ranges from Hawaii to Alaska? Okay. The research program that over at UH Manoa, at the Marine Mammal Program, the main thing that we try to do is to do really good biology and ecology and use that information to inform management. I'm a very firm believer of that. We do science to inform management. I think that's a really, really important role, and part of that is stakeholder and community engagement. So opportunities like tonight is really wonderful, so thank you. Okay, the quick 101, I'm sure you guys all know this. The humpback whales that you guys have here mainly migrate between Alaska and Hawaii, and that's a 6,000-mile return trip. In Hawaii, there's about 10,000 whales, roughly, and in southeast Alaska, about 3,000 of those whales are seen, okay? Now, once they spend their foraging time up there, when they leave, many of them come down here, rest, give birth, mate, and then they migrate back up again. But when they leave Alaska, they don't feed again until they come back up again. Well, I haven't fed for about an hour or two, and I'm already starting to get angry, right? So imagine the pressures around some of these animals that aren't going to eat for 4 months and have to migrate and give birth to a calf, fatten the calf up, and go back up again, right? So these are the kind of pressures that are on these animals. And it's this that we're trying to understand. So we are using some newish technology. 10, 15 years ago, we didn't have a lot of this technology, and it's really allowing us to get to some of these answers that we haven't been able to get before. So what I'm going to be talking about today is how we're using UAS, or unmanned aerial systems, or drones, to quantify body condition. And then I'm going to be talking about how we're using suction cup tags to understand how the animals are feeding in Alaska. And a project that we're starting in a couple of weeks here in Hawaii is to try to quantify how much time calves spend suckling from their moms and correlate that with the growth and body condition. So I'll try to explain how we're trying to get at that. So here we have the different collaborators. Again, really critical. Everybody has a very important role in this work, and I'm very grateful to be part of that. So let's talk a little bit about the migration and what we're trying to do exactly with the body mass. So you're not going to feed for 4 months, you're going to lose some mass, right? And how are you going to be able to do that, and how you quantify that is to go out and try to find as many whales as you can in Alaska, and I'll show you exactly how we do that. We use the drones, we can actually quantify how big the whales are in cubic meters, and then we try to find as many whales up there. We do the same thing down here in Hawaii, and then we do it again and again, and link to long-term historical records of where these animals are migrating. The three main things that we're trying to quantify is, well, what's the changes over time and space? And we're trying to explore that with what are the large oceanographic features that are happening. It might be a good year for herring up in Alaska, and then there might be a year or two later you see really fat whales, right? So we're trying to correlate it with the big picture, and then we're trying to compare the body condition of this population with other populations around the world with colleagues that are doing similar efforts. And that's going to allow us to say whether the humpback whale population here are skinnier and more malnutrition compared to these other populations that are doing pretty well. I don't know about you guys, but sometimes I feel like that one up top, right? Sometimes I feel like this. Around Christmas time, it's more like that. Your body condition tells you a lot about your state, right? Sometimes we can use these metrics to figure out whether an individual or a population are doing really, really well. In the animal kingdom, the bigger, the stronger you are, the more likely you are to reproduce, but also the more likely you are to be able to migrate these very, very large distances, right? So if you're able to quantify the health of an organism based on body size, you can say something about its health and its population health. And that's basically what we're doing. We're trying to quantify how big or small these animals are and compare it to the mean of the same population and other populations. I just want to acknowledge my previous postdoc, Frederick Christensen, for really pushing this work and showing us how to quantify this. But basically what we do is basically we take pictures of whales and we take videos of whales and with flat lenses, so there's no distortion, and then we can use the pixel sizes and translate the pixel size into actual measurements once you know the height and how high your drones are. There's some custom written software that allows us to measure the width of animals up and down the body length. So pretend that the tail is your feet, the rostrum is your head, and then you're measuring different widths as long as you go. Right? And for humans, we're going to be most likely biggest around the waist, and that's also what we have for whales. Okay? So every single 5% down the body line, we can measure how big these whales are. Now this next slide is how we calculate it. So we go from a two-dimensional image to a three-dimensional volume metric. Is that we make an assumption that they're cylindrical, which isn't quite right, but it's a good approximation. We calculate based on the area. We get these slices. We essentially fictitiously slice a whale in many slices and add the volume of all those slices together to figure out how big they are. And that tells us something about its volume. Let's see. Now, these are not humpback whales, you know that. These are gray whales, but the reason why I'm showing this example is that we're not allowed flying a drone over a drone in U.S. airspace, but Mexico, they're not as strict. So we did it here, but basically this is what we do. We fly the drones out. Again, we have very precise altimeters with flat lenses on them. We get up above them, and then we start videoing them. And then when we're on top like this, we can basically take snapshots out of those videos and see how wide they are, like we did in the previous slide. So we started this project right after the meeting that Jens talked about. So in 2018, both up in Alaska and also here in Hawaii. And today we've already measured, we just started, we've already measured more than 1,000 individuals already. And many of these animals we know the sex of, and quite a few of them we also know the age of, which means that we can analyze our data based on age and sex as we move forward. Now this is a hypothetical scenario of how the body mass of a humpback whale looks like over 1 year. Okay, so just work with me here. So imagine that they just left Hawaii, they've now just made it to Alaska, okay? So now they just on average make it to Alaska in early April. And relative to other parts of the year, that's when they're going to be skinniest, right? They hadn't fed for 4 or 5 months. So they're relative poor condition. Now they stay out there on average till end of October, November. So we would assume that they increase and they migrate back to Hawaii. And as they're here, there's a lot of physical activity going on, and particularly the females are lactating, so they're losing even more energy and more body mass. They'll reduce in size, and then they'll migrate back up again. So that's kind of the annual cycle that we predict, right? Now, I mentioned that we've already measured over 1,000 animals, but Martin Manoa, who's a PhD student, who's actually the one that's crunching the numbers behind this, I just want to acknowledge Martin, took some preliminary data just to kind of show you what we're looking at, and how much energy and how much body mass we change over very short time periods. So again, this is the hypothetical scenario, right? Now this is changes in volume on an Alaska feeding ground. So I'm just going to step through this one. This one was taken in November. This is about 30 animals again. In November. So that's here, that's just before they leave. So that's when they're as fat as they're gonna get, right? We measured about 30 here, and this one down here is in April. So that's just after, so they've left, just before they leave Alaska, they've done all of this, and now they've just come back to Alaska. So we go from there to back here. And on average, and I haven't split it between males and females here, but on average, they lose 32% of their body mass. So a third of your body mass just like that. Okay? Now, I think quite a lot of us would like to lose a third of our body mass that easy, right? So that's a lot of energy that's really moving around, right? Now, this is work we did last year. These are the adults here in Hawaii. We had it in January, so again, just to go back to here. So this is, this is January, so we're here early. So they just arrived to Hawaii, and then we have them in March, later in the season. And you can see here, males and females, when you calculate this is about a 20% body decrease in the 2 months, for these 2 months. So even though they're not migrating, all that activity that Jens talked about, they're using so much energy and they're losing that, right? So just go back. So this is the volume, it's cubic meters, right? So that's based on these cylindrical slices that we're looking at. So it's cubic meters of mass. So if we look at, this is calf, this is really interesting. So I've lumped this right now, we just had 11 just to start with. So this is January, February, or March. So at this stage, this is preliminary. So this could have been early January or late March. So that's why you see a wide range here. So that's, oh, there we go. So this is from here, middle of the breeding season, and then they come up to Alaska and they're about halfway through, and they put on 350% of their body mass in 6 to 7 months. So they really stock up really fast, right? Now something interesting, last year, just like you heard Stephanie talk about, there was a very newborn calf yesterday, or a live birth. Last year we were lucky to measure an animal that was born within an hour, thanks to Ultimate Whale Watch. And that animal there, we measured, sorry guys, that animal there was measured to 0.35 cubic meters. So that's all the way down here. So these animals that we've measured here are probably already a month or two old, right? And so when they're born, they're all right down here. That's how low small they are. Just put it into context. Okay, so we're starting to get a handle on how much volume that they're changing. Fortunately, we are working with colleagues around the world, both in Antarctica, in Australia, and then here, on humpbacks, different populations with segments to see how these body masses change and are they different for these other populations that we didn't see these declines in. We're also working on right whales and gray whales to see these same kind of trends if there are. You might have heard last year there was what's called an unusual mass mortality event of gray whales off the west coast of the U.S. And those animals were extremely emaciated, and surely enough, our data showed that those animals were clearly much skinnier than they had been for the 3 previous years. So it is a really good indicator that there's something happening in the environment. So we do think this is a good approach to get at health at that level. But how do you grow, right? So we want to figure out, well, what is the rate of intake to figure out when they get large in Alaska. So that's where we're looking at 2 different things, or one main thing is to look at the foraging rates and how fast they put on weight. Now this is a bit of an extreme example. Many of you might have heard of this bubble netting activity, where humpback whales blow bubbles to encapsulate prey, and then they go up through the water column. I should highlight here that that's not the normal, so the stuff that I'm showing you now is not what normal humpback whales do. There's a proportion of them that do it again and again and again, and it's quite fascinating. And these animals we concentrated on in July, and we're starting to get good ideas of the foraging rates of these animals, and that's what I'll present to you now. And that's using both the drones, but also some tags that have suction cups on them, so they don't pierce the skin, and then they have video cameras and all kinds of accelerometers inside, which I'll concentrate on now. Here's a tag that's just been put on a whale. These are what's called D tags, a little bit different from what we're going to be using here next week. But basically, the suction cup tags, and they have all these fancy accelerometers and computer bits in them. They have hydrophones, they have depth sensors, and then they have sensors that how you move in 3-dimensional space. And many of you guys might have Fitbits, so think of it as a Fitbit for whale, right? So I'm glued to my iWatch, and I look at how much activity I do, and if I don't do enough, my wife tells me to get out there again, right? So it's one way we can look at what these whales are doing. It's the exact same thing, okay? So we're putting Fitbits on whales. Think about it. Here's just an example. They're quite small. They're about this size. And if you're a whale that's 25, 30 ton, 40 ton, that's like a fly sitting on you, right? Here is an example of how I'm not sure if this is going to work. Let's give this a go. Here's an example of putting it on. Does it work? Yeah, this is bubble netting animals that have just come to the surface, and we're just approaching. This is a group of 16 whales doing the bubble netting, and we're just approaching now to get one of these suction cup tags on. You can see a long pole, carbon fiber, which is very light. The tag is out on the end of the pole, and then we wait. Oh. And off goes the Fitbit. You can time them to release, or if they're very active, they'll pop off by themselves. Average deployments are about 12 hours for these tags that we're using, which is fine for short-term indicators of what we're trying to get at. This was really interesting. Let's see if this works. This is now using our drones from the top, which is on your right-hand side, and this is the tag on the humpback whale facing forward. The first thing my daughter said, is that camera pointing backwards at that? so it is air coming out the front. Here we've just sped it up, but this is when they're making these circles. These are individual whales not working cooperatively for the herring, but this is more on krill. You see we sped it up 3 times here, and you can see linked, it'll come up the tag on the top one. And you can see the left pack bending, and you can see how they turn around. Now we slow it back down again, and you can see the mouth open as it's coming up through the center. And then you see up here, it comes up to the surface. Now the next one here, that's the cool footage, but the neat data that comes in is this. This is the cool bit. This is where I get excited. So this is all these sensors that we have on the tag, right? This one, so we have it on the pole right now. So if you look at this red line here, is the time, okay? See that moving ahead? Right here is when the tag goes on the whale. You'll see that, and then it dives down. Blue is depth, so that's meters. So this is about 90 feet down here. The green one is speed, and the purple one is what called jerks. It changes in speed, if you will. So you'll see it pop on in a minute, and then after that, I want to take you down here. This is what really tells us what the animal is doing. So this is what's called pitch, roll, and heading. Heading is compass bearing. So think about it as a compass bearing. Let's just get this tag on in a minute here. So now you see that. See the red line? There we go. Up. And off you go. And now you'll see the whales start going to the bottom here, yeah? So now we start looking at the sensors. This was the stuff that's telling us. Now, previously we haven't had cameras, we just had the sensors, but now we can corroborate what's on the video with actually the sensors themselves, right? So what's really interesting, and I'm going to fast forward in a minute, but the blue line here is compass bearing, okay? This goes from minus 180 to plus 180, so 360 degrees. And then what you'll see here, the red is roll, and the other one is pitch. So roll is if you're going like this, and pitch is if you're going up or down, okay? I'm just going to try to forward this one a little bit, see if we can get to interesting bit here. So now you see, right there, that's the first time it starts exhaling. We can see when they start producing the bubbles. We know what depth that's at. And you will see now, look at the blue line now. As soon as they start blowing the bubbles, about 15 seconds after that, they start their 360-degree turns. You see that here, the blue line? So that's telling us now that it's been going straight, it starts blowing, and just when that starts doing its 360-degree turns. And if you count how many turns, 1, 2, 3, 4, 5, 6 turns. And when you see those drone videos, you can see those 6 circles up there, right? Now, the interesting thing about this stuff here is that we can actually start measuring how much energy that these animals spend when they're doing this. You can start relating that to energy consumption, because if you look at expiration rates, if you get someone, an athlete on a treadmill, and you put the oxygen mask on, you measure how much oxygen consumption there is, and you can then start looking at what's called metabolic rates, right? So we can come up with estimates of the metabolic rates and what it costs to forage, and then you can start comparing these different foraging tactics to animals that catch, whales that catch herring, whales that catch krill, and whales that catch other items, and then you can look at the prey items themselves and how much energetic value each of these prey items have. You see where I'm getting at? You can start piecing all these pieces together and to get at this bioenergetic model that we're trying to get at. So this is what's called a track plot. So this is, let's see if this will work. Oh. So this is cool. There's a little bit of what's called drift in this, and we haven't quite figured out why that's happening yet. Come on. There we go. So this is an animation on what the tags are doing. So they go now. So you see they aren't exactly stacked on top of each other because this is called dead reckoning. We don't have GPSs on those tags, so it assumes where you put the tag on and where you take it off, and then it does calculations to kind of backtrack where it's at. So if we didn't have the drift, those stacks would be straight on top of each other. But I think we can change out to new tags because there's GPS on them. But what you see here is that I think we zoom out a little bit, and you can start seeing how they're using space in 3 dimensions, right? The plan for the next year up in Alaska is to do prey mapping with echo sounder to look at where the prey fields are, and then link that with how the whales are using the habitat. Okay. So that's how we're looking at prey consumption for this particular prey type. The last piece of the puzzle that we're trying to do here in Alaska, which again we started in a couple of weeks, is to look at how much time calves need to put on to suckle to get big enough to be able to migrate back to Alaska, right? And then we're going to correlate that with growth in these calves. Now we have done this in Australia with different kinds of tags. The west coast of Australia, which is doing really, really well, that population that migrates up and down here, that's called Stop B, they were hunted down to only 270 individuals in the whaling area. After whaling stopped, that population has done an incredible increase of up to 8 to 10% per year. And if we go back to 2012, so almost 2009, 10, 11 years ago, that population was estimated at 30,000 individuals. So if we assume roughly the same increase, that population is probably more than 40,000. But one of the assumptions of why that population is increasing at a higher rate than any other population is because in Western Australia you have very undisturbed breeding and resting habitats. So there's very, very little disturbance in some of these areas. And one of the things we wanted to do was to quantify why are they doing so well in these breeding and resting grounds. And we did the exact same thing. I'm going to forward this a little bit. And Mark and Adam tells me not to expect these very cooperative whales that we have in Alaska here. But that's a mom and a calf on the left. Again, these suction cups, which is exactly what Mark and Adam are doing out here right now. Put them on the calf. Within a minute or two, they're back to resting again, and then you can start looking at these things. And off we go. So some results that we got out of this, and here we can only write presumed suckling because we're looking at how these accelerometers fit, and we say that if they're in a certain position, we presume they might be suckling, but we can't say for sure. What we're going to be doing here this year is, because now we have the cameras, we can actually see if they're suckling or not. But in Australia, each one of these lines here, the blue ones are females lactating, and the ones on the right are calves. Take home message here, on the resting or breeding habitat in Australia, the moms rest for about 8 hours a day. They just lie there kind of thing. And the calves suckle up to 1/5 every day, so about 3 hours, 4 hours a day, they just suckle. So we're going to try to do the same thing here in Hawaii to figure out that whole cycle. So overall, what are these tags and drones telling us? Well, we're going to be able to start looking at feeding rates. We're going to be able to corroborate that with how fast they're putting on condition or not. We can look at what prey types are better, as in this prey species might be, if you eat those, you might put on more weight, have burgers instead of salad, right? And then trying to link that with all these other populations that we're studying all over the world to be able to say why Hawaii's population is doing better or worse, if you will. So, thank you very much.
Yes. Okay. Thanks, Lars. That was great. And it's interesting, you were mentioning losing 30% body weight, and I'm happy to say that in a year I've lost 30% of my body weight. Probably a little bit more than that. Thanks WW and spin class at Hilo. But I'm very happy to be here. Aloha, everybody. Happy to be here to talk with you. Maui is one of my favorite places in the Hawaiian Islands. I came to Hawaiʻi when I was 20 years old, way back in 1983, and made it my home. And I've been coming to Maui to study the humpback since 1996, which is quite a long time. And I've been going up to Alaska since 2007 to study them in their feeding grounds. So I'm very happy to be here to tell you a little bit, round things out from Jens and Lars, and talk a little bit about comparing indicators of fertility and stress in humpback whales in association with body condition changes. And as Lars said, body condition does change when we're here, and so it's important that we not only document that, but that we understand the type of stress that animals incur as they're going across the season in between Alaska and Hawaii while they're fasting. And so that's part of what I'm helping out with here. If I can have everything going. Okay. Our studies with humpback whales actually go back to 1976. Some of the first aerial surveys of humpback whales in the Hawaiian Islands, and actually that's what I'm going to be doing tomorrow, is the first of 3 aerial surveys over the Maui Nui region. We go up in a Cessna 4-seater plane, and there's the driver of the plane, there's a recorder, and then myself and Mark Dicos, who lives here on Maui, who's one of our students. We're each looking out one side of the plane and counting whales, and we're doing transect surveys similar to what Jens was saying in the boat. We do it in the air, and so we go out 9 nautical miles from each side of the Maui Nui region. So we're looking at in the Au channel, the Pailolo and the Kalohi channels, but we're also going down to Penguin Bank, and then we're going on the north side and all around the whole 4-island region. And we're counting the whales there. We'll be doing that in another 10 days and another 10 days. And we're going to be comparing those numbers back to last year, when we conducted the same type of aerial surveys. And the previous surveys were way back in 2000. So we're trying to get an understanding from the air of what's going on. These are, aside from the aerial surveys, these are some of the projects that we've been involved with over the years. Up here on the left, you see a CritterCam tag. We were working with National Geographic to deploy these tags. back in 2008 and 6 and 5 on the whales to see as well as to learn about their behavior. And this is focused on competitive groups. We do a lot of documentation of the whales in terms of the behavior. That studying on the upper right there is we're using rebreathers to dive with singers to measure their sound fields and to learn about song. And then down here, I'm doing a technique we developed back in 2000 called underwater videogrammetry, which is to measure the size of the whales underwater. And we learned a lot from that project about the relation of body size to behavior and behavioral role in Maui waters. But I'm thrilled that we're now working with drones because 500 whales at a time, it took us years to accumulate those types of numbers. So it's an exciting project. And as I mentioned, we also study the whales up in Alaska in the feeding grounds. And our project actually goes back to 1980 through 87. And then in 2007, I was giving a talk in Maui, and this captain of this boat came up to me, happened to be attending the talk, and he said, you know, I'm up there with my wife. We have this large 80-foot long boat up there. Would you come up and start studying with us? And so I did. And it turned out these were the same waters that my mentor had been studying way back in 1980 through 87. So that was very exciting to see a lot of those same whales. Oops. I see how this goes. A mainstay of our and many projects is tail fluke photography. We've been doing it since 1976. The undersurface of the tail fluke, as you know, is its fingerprint, a combination of pigmentation patterns and the serrated edge. And that's how we tell who the whales are. Through dutifully photographing these whales year after year after year, we've amassed a massive archival catalog of over 22,000 observations of some 5,000 more individuals. And it's allowed us to do a lot of things. There's a lot of power to that in terms of tracing the life histories of the whales and looking at their social networks with each other. For example, this is a whale that was first sighted in 1972 in Lynn Canal, Alaska, and we saw it in Frederick Sound, Alaska in 2015, some 40 years later. So we can trace these life histories in the different waters. And you can see this whale wasn't just in Alaska, but we saw it off the Big Island in 89, 91, 94, and in Maui and subsequently. This is an example of one of the published works that we did, which was looking at site fidelity to the Hawaiian Islands. And so this is a whale that, look at all those times this whale is coming to Maui and being seen as an escort, sometimes as a singing escort. Way back, we first saw this whale in 1978, and then through 2007 and beyond. I mean, the slide ends, I couldn't put more on it. And we could also look at whale residency in the Hawaiian waters, which is directly dependent on body condition while a whale is fasting and also on its reproductive state. So here you see a mother. That's the label up in the left-hand corner that we have, January 7th, 1999, and then the same year, 10th of February, 99. So the calf is older. We know it's a match. We can look at the depth that the whales are occupying. What we showed in this study was that as a calf ages, the mother starts taking it out into deeper waters. The important point here is that we can look at whale residency. And so here's an example of a publication we did from 1976 through 1996, looking at residency differences in different behavioral roles. And what you see here, the yellow bars are females without calf. Once those females become pregnant, they're out of here. They're going to leave and start heading back up to feed. But there's a big difference with these adult males, you see that's in blue, and mothers who are in red, and weeks are on the x-axis. And you see some of these mothers stay as long as 51 days. We've documented adult males out to 76 days, all here. And while they're here, those adults aren't feeding, so they're losing body condition. And in theory, they're becoming stressed from it. So body condition can be affected obviously by fasting in a breeding ground, but it can also be affected by energy expenditure during the behaviors that you're doing during normal activities. So we know that males in the breeding grounds are competing for access to females, right? For mating opportunities. We know that they prefer females without calf over females with calf, although as the females without calf start leaving and it's harder and harder to find them, what we found is that the males switch over to these mothers, and so you start seeing these large competitive groups surrounding mothers later in the season. Just to let you know how ferocious that aggression can be, here is a little video. See if this works. This is a critter cam on the back of a humpback whale in a competitive group. It's on the principal escort, and what you're going to see is a challenger come in and start trying to displace that principal escort. So it's on the back of the whale, it's headed forward. It's turning slightly. And here comes the challenger. This is all happening underwater. And you see all the skin is being sloughed off. And it looks like, okay, well, that principal escort survived that hit. What you're going to see in a second is that the challenger comes back. There he is again, and he's going to do a body slam into the principal escort, and they're basically head-to-head at this point, underwater. And then he's going to kick him twice with his tail flips. And now what you see is that there's the challenger now blowing the linear bubble trail, and they barely can see the female up there, and so now that challenger has become the principal escort. The point being, a lot of energy is expended by these animals in competition. We've also found, and published recently, that that mothers aren't just sitting there sometimes quietly, but often they are so-called harassed by males who are prospecting for mating opportunities. And this harassment takes place, or part of this is in energy expenditure from the mothers. So what you see here is the number of escorts in calf pods on the x-axis. And as it moves from 1 to 2 to 3, there's a significant change in the swimming speed of mothers with their calves. So mothers are expending more energy when there are more escorts around. And as a consequence, what you see in Maui waters is that mothers sequester themselves or segregate themselves into these shallower waters, which is why it's so important to keep those waters quiet, to protect them. But more energy being expended. So one of the questions we want to ask in this collaborative effort is, how does stress and fertility vary in humpbacks as body condition changes seasonally? This, by the way, is a whale I call dog face. I don't know, if you look at that left blade right there, doesn't that look like a face to you? Or is it just me? Anyway, that's dog face last year, March 7, 2019, when we were all out working together. And then this summer, up in Alaska, around Five Finger Lighthouse, I was up there with a team of people, and they kind of thought I was strange because I yelled out dog face, and this whale was feeding in a bubble net feeding gourd, similar to what Lars was talking about. And I just have to say, I was on the boat today with Mark, and we were putting tags on humpback whales to learn more about them, suction cup tags. And I don't know if you've ever heard of this app called Happy Whale, but it's basically a matching program. And I got a signal on my phone that said dogface was just sighted yesterday in Maui. So he's returned. There's a lot we already know in mammals about the physiology of the stress response. So in response to a stressor, something called the HPA axis is triggered. And through a cascade of events, and from the adrenal glands, we've got this production of glucocorticoids. And you may have heard of some of these like cortisol or corticosterone. And what these do in the body is that they alter behavior, they increase blood glucose, they inhibit growth and reproduction, and they suppress the immune system. So it's an immediate kind of response to acute stress. And you can see that there's also a negative feedback. So that negative feedback stops that production, so it's not a permanent thing. But if you've got chronic stress, you've got chronic elevations of glucocorticoids, those can be detrimental to endocrine function and ultimately to health. And so what we're interested in is establishing some baseline levels of stress in humpback whales naturally, so going back in time prior to this heat wave, and then looking currently at what the levels of stress are now. So to look at stress, what we do is we take small biopsy samples of the whales. This is samples of skin and blubber. It's about half your fingernail. And we use a crossbow with a stainless steel tip that's sterilized. You can see in the picture here, a picture of the arrow with the tip on it. That's just gotten a sample, and here's the sample right there in the baggie. And so through this, we're looking at testosterone, progesterone, corticosterone, and cortisol. So the first two being steroid hormones that are going to give us indicators about fertility and pregnancy in females, and the second and the third and fourth, stress. And so this is some data, this is some baseline data from a recent publication that one of our graduate students, Kelly Cates, did with her mentor, Shannon Atkinson at University of Alaska Fairbanks. And we just published this last spring. This is the SPLASH project, which we were part of from 2004 to 2006. So this is baseline data. And this is looking at testosterone. So here you see Hawaii versus Alaska, and you see that testosterone is significantly greater, as you might expect, in the breeding grounds than in the feeding grounds. Here you see the seasonal variability in testosterone levels, on average with the highest in the winter and spring, right? Compared to the lowest in the summer. But what's interesting is you see a ramping up in the fall of this testosterone. And coincident with that, what do we start hearing in Alaska at the end of the season? We start hearing little bits of song. And we know that the males, therefore, are increasing their testosterone levels. They're getting ready for the breeding season, for migration in the breeding season. But what we also learned is that humpback whales are what we call capital breeders. And they do not have, the males do not have the same testosterone levels across the whole breeding season. They start out in January, as you can see here, in the early months with high levels of testosterone, and then those decrease across the breeding season. And that was new information as well. In fact, I broke this down into principal escorts, secondary escorts, and single escorts to mother calves, and you also see in all three cases a significant decrease across the breeding season. Even if we look at individuals, so each of these paired bars represent an individual in Maui from first to second sighting, right, across that residency, and you see for each one of them, testosterone decreases. The next steps, we want to compare testosterone and progesterone levels pre and post heat wave. So Jens mentioned that in 2016, we had this kind of a troika, a trio of events going on. We had a very strong El Nino. We had something called a negative Pacific decadal oscillation, which kind of was a protracted heat wave. And then we had this blob, if you read about it, in the North Pacific heat wave. And that combination didn't just affect humpbacks, it affected the cod fishery in Alaska. There was a gigantic muir die-off, common muirs up in Alaska. It affected lots of the part of the marine ecosystem. So what we're interested in is looking pre versus post heat wave and looking at some of these reproductive parameters like testosterone and progesterone levels. We also want to compare stress indicator levels pre and post heat wave, and then we want to relate the stress indicator levels to body condition, working with Lars and Martin, and residency length and fertility, all working together as a team. We also are very fortunate, not only are we working with Shannon Atkinson in her endocrinology lab up at University of Alaska Fairbanks, but also Christy West at Hawaii Pacific University here in Hawaii. And so Christy is going to take some of these samples, and she's got a histology lab. And one of the interesting things is that successful reproduction can be directly mediated by body condition. And Christy's been looking at this assessing body condition technique using blubber adipocyte area index. These fat cells, which store lipids, it turns out that instead of the number of fat cells increases, what you're looking at is the expansion within a fat cell to accommodate fat storage. And so what Christy has done is she's basically found striking distances in AAI in emaciated versus robust stranded melon-headed whales. And that is interesting because that may be something that we can look at with humpbacks as well, skinny whales versus robust whales, and looking at their fat cells from these biopsy samples. And we're also going to be looking at, with Christy, stable isotopes to try and understand a little bit more about the prey limitations of humpbacks as they're migrating, what they've been feeding on, and how versatile they are. To date, now working with Lars and Pacific Whale Foundation in 2019, we collected 20 biopsy samples, and in this January that we just had, another 33 will be out again in March, and trying to add to this. And this is a long-term project, trying to build up these samples from animals in different behavioral roles so that we can look at stress and we can look at fertility. Through all of these studies, our goal really is to promote a healthy Central North Pacific population of humpbacks for all of our generations, and to recognize that, you know, we are a community here. We have social networks that are important to us, and so do the whales as well. And so this reminds me of a talk I gave last summer in Alaska to an audience similar to this, where I talked about that we are the stewards of these waters, and we need to protect them for future generations, but also for the humpbacks themselves, and to learn about and understand their lifetime histories, their social networks, so that we can all share the oceans together. Mahalo.
So the Maui Marine Resource Council wants to announce a new program starting in April. It's the Maui Marine Research Council Weight Loss Program. We're going to swim to Alaska. Okay, let's take a few questions for our esteemed scientists. Amy will bring the microphone, and Meredith will take my microphone, and we'll let our scientists respond. Thank you.
Any questions? Raise hands. Here, okay.
So, you have not established yet what the normal growth patterns are for the calves? I mean, you're just starting to do that now.
So the question is, do we know what the normal growth patterns for the calves are? We have it across population. When I say that is, we have it as a trend, but the key thing in which what we hope we can do here is follow the same individual, have multiple sightings and measurements of the same individual. And what we have is we have averages across animals, so we have trends, but we can't say for an individual. But I think within another 2 years, given the sample sizes that we're getting, I think we'll get pretty close. Yeah.
I would just add to that one of the things that we've been talking about doing is to take some of these measurements of very young calves and back calculating when that calf was born. So from our early videogrammetric work, measuring the whales underwater, it looked like some of those whales were actually born in November, or maybe even in October, right, prior to seeing them here. And so it's interesting to see, you know, if we combine both efforts, what are we seeing and have those trends changed over time?
Yeah.
So just one more comment. Because we have a couple of measurements now of calves that have literally just come out of moms, we know how to ground truth that day 0. So that's, the first one was 3.96 meters, the other one was 4.01 meters. Christy West just necropsied a humpback whale off Oahu with a fully termed calf, and that was 4.01. So if anybody asks you what's the size of a newborn calf, it's 4 meters, exactly.
Yeah, hi, my name is Jeff. I spend a lot of time on the water observing whales, and I've also heard from some other folks who do tours out there that anecdotally over the last 5 years or so since this decline, we noticed that competition pods are a lot less aggressive. And so based on what you said about energy output, and also the fact that some individuals in Alaska are not showing up in their regular spots. Initially someone suggested that possibly some of those older males that might drive that kind of competition might not be making the journey. I just wonder what your thoughts are on that based on energy output and what that might say about that.
I'll start. One of the big questions, particularly for 2016 or 17, was because we're seeing fewer animals here doesn't mean that they didn't make it. It could be they've just gone somewhere else, right? So are they using the Hawaiian Islands differently, or did they go more off the west coast of the U.S.? We just don't know, or in Mexico, for example. So because we saw that drop doesn't mean that they died. So I think that's an important point to make. And that's why large-scale projects are really important when you're comparing these things. What we did see in Australia for body condition changes between males and females on their breeding grounds, much to our surprise, the males almost lost as much as the females did for lactating females. The lactating females certainly lost more, but males also lost significant amount of body mass. If you want to pick up on that.
I would just add that one of the things that drives competition and these super competitive groups that you see is that, as I mentioned, as the coveted females, the ones that the males prefer, the ones without calf, as those start getting pregnant and start leaving, it's harder and harder to find those females. And so the males turn their attention to the remnant females, either the ones without calf or the mothers. And that's when you start seeing towards that second half of the season these gigantic pods and lots of them. But in 2014, 15, 16, what started happening, and 17 as well, is that the season either never really peaked very high or was truncated, not giving enough time for it to kind of play out. Additionally, it's very possible that some of those whales were in poor body condition or sought food in different areas than the traditional ones and didn't bother migrating down. So Shannon Atkinson, who is at the University of Alaska Sitka, she's for years been documenting whales who don't appear to make the migration down. In other words, that they don't necessarily have to migrate. And certainly if they're in poor body condition or they're still searching for food, maybe they don't migrate. But one of the things that we can do with the archive that we've established and working all together as a team is we can start looking at who are the whales who came down here in 2016 and 17. And were we also missing some of those older whales? You know, what was the demographic profile that we saw back then? We have the ability to do that because we have whales that we've been tracing for 40, 45 years now. That's the value of that catalog.
All the presentations were absolutely fascinating, but I'm still left wondering how they explain the drop in population.
Yes. one of the things that we're hoping to do is, it's going to take, if you had 2-3 bad years, those things will take time to spill over. It's a cascadal effect, right? So because we weren't measuring these, for example, body condition measurements in the 2 years where we really plummeted, we don't have those metrics then. But we'll have metrics now that we can compare to other populations. That will tell us whether they're healthy now or not. The key thing, if there are no changes there, is to compare these photo ID records with other populations through this app that Adam told you about, that's called Happy Whale. My guess is that a lot of those whales that we didn't see here and in Alaska are going to be found in other locations. I think it's a redistribution of these animals. Because if there was a drop of 50 to 60% that some of these anecdotal data is telling us, we would have seen a lot more whales on beaches and coastlines, right? There are estimates of what are the carcass recovery rates from other areas. So for the Gulf of Mexico, there's a paper out about 5-6 years ago to look at 12 different species and look at what are the carcass recovery rates of some of these animals. And compared to Hawaii, the Gulf is much more enclosed, right? And the average carcass recovery rate was about 5 to 6%. So only, depending on species, 1 out of 20 will land on a beach. But if you have a decline of 50%, even when you have lower carcass recovery rates, we would have seen a lot more whales on land. So I guess my take-home message is, my thought, and I think a lot of us think, is it's been a redistribution. And until we get all of these catalogs linked through this Happy Whale, that's where we're going to find the answer.
I just want to add that, 3 of 38 researchers and managers came together and we talked about one goal. And I don't think you're ever going to get the answer if it was definitely this. It's going to be a cumulative effect of a lot of different things that are happening, but we're now in a place where if it happens again, we have the data being collected to be able to answer it more quickly. And we can also use the data we're gathering now to try and look back at some similar conditions in that time we saw the decline.
I would just finalize with, if you remember the slide that Jens showed, I think, about Adam Frankel and their team's shore-based work off the Big Island. What they looked at was these 3 factors that I mentioned over that period of time. El Niños, Pacific decadal oscillations, whether they were negative or positive, and this heat wave. And so, of course, there have been El Niños before, and there have been negative PDOs, or Pacific decadal oscillations. And you would see from their shore-based work small deviations, fluctuations in numbers. But it was really when this blob occurred, that combination, where you saw that dramatic drop. So there is still a little bit of the ability to tease out some of these factors. And this trilogy of coming together, this heat wave with these others, seem to, again, not just affect the humpbacks, but really the entire marine ecosystem.
So I had a question. I attended a conference in Washington State, Port Townsend, and they showed a video on the correlation between the dams and the whale populations up there. And I'm wondering, are you collecting any data on fishing, dams, and that type of stuff as far as energy conservation and the actual fish that are involved that they're consuming?
So that would be in Alaska, right, for the foraging areas. So our colleague at the Alaska Whale Foundation is doing prey mapping up there to look at prey fields. I think you're talking about the southern resident killer whales and the salmon, which seems to be the major issue, is that they're not getting enough food, basically. We talk about these oscillations and so on. One of the major factors for that is because of changing prey distribution, right? And you certainly see in Alaska, there's areas in fjords where you used to have lots and lots of herring. We're simply not seeing that anymore. But think about the coastline of Alaska and how complicated that is, and how you go out and quantify large areas of prey. It's a really daunting task, but prey is a critical factor in trying to figure out what's happening.
Thank you.
I would just add that in 2016, 17, 18, when we were up in our area of Southeast Alaska, we had hardly any calves. And we had in 2017 and 18, few whales. For people coming up to see the whales, it was exciting because every time we went out, we saw cooperative bubble net feeding on herring. But we hardly saw any krill. And we saw hardly any krill feeding. And in context, going back 3-4 years, in one of these areas, Frederick Sound, you would sometimes see 400 whales just plowing the fields of krill back and forth. So it was very unusual to not see that. I'm happy to report that this past summer, when we were up there, we saw a lot of calves. And we all of a sudden started seeing krill feeding, and some of the krill feeding that Lars was showing with using bubbles for that. So the two areas are tied together. You can't look at them in isolation. We've got to appreciate what's going on in our sister waters up in Alaska too, because that's where our whales are going. The health of those waters affect the health of our whales.
Thank you.
One more question. Okay, this is working. How do the moms decide when babies are in good enough condition to make the swim back?
That's a great question.
That is a very good question. So, mammalian reproductive biology dictates that a long-lived female will forego its calf to make it herself, on the assumption that if I'm a mom, if I live to reproduce 5, 6, 7, 8 more calves, right? So of course mom wants to hold back until the calf is big enough, but if the calf hasn't made it, she's gonna go anyway. Because if I maintain my body condition, I'm gonna reproduce hopefully 5, 6, 7, 8 more times. So it's a bit brutal, but that's
And calf mortality, there is data on calf mortality that Chris Gabriel, one of the people who studies whales up in Alaska and on the Big Island, has published on, and that's about 18 to 20%. So for every 100 calves, about 18 to 20 don't make it. And we've seen, and maybe some of you have seen, sometimes in the waters out here, we'll see calves without a mom around. And so that's kind of what Lars is getting as well. But many of these moms will, as you saw in the residency pattern, I mean, they have these long residencies down here, and at minimum, I would say, that female who was down with her calf 51 days, that was just when we happened to photograph it first and happened to photograph it last. She could have been here longer. So there is a drive, as long as your body resources last, to remain with your calf and to beef up that calf. And just closing, the whales, of course, are not all migrating down at once. They migrate in what has been termed a migratory parade, which is conditioned by their sex, their reproductive state, and their age class. And so the last whales to migrate down are the pregnant females, on average. And why are they staying up as long as they need to up in Alaska? To build up those body stores. And females on average are 5% greater in size than males, humpback whales. And there's a good reason for that, to have those big body stores.
So are orphan calves do you ever try to rescue the orphan calves?
An orphan humpback whale calf will unlikely be adopted by, unlike like bottlenose dolphins, where sometimes you'll see adoptions in the world occur, is unlikely. What you see is that the calf will try to associate with whomever it can. Sometimes the whales tolerate it, sometimes it doesn't. Years ago, I co-wrote an op-ed for the Maui News, I think it was, or it could have been the Honolulu Advertiser. We had a series of calves like that way back in like 1996 or 7. We were talking about, would it be possible to cordon off an area to help try and raise the calf. They've done that with gray whales twice, tried. But it was an idea. But it's part of the natural life cycle too, right? So.
One more question?
I think we better let our scientists go home, and we'd like to thank you again so much for coming out and being a great audience and showing your care and respect and enthusiasm for our marine life that we're all trying to protect. So thank you again, and maybe we'll see you next month.